All right, so this is our last section. Inferences on two means if they are independent samples. Clearly, we're going to have to look and read to make sure we don't have dependent samples and we know the difference. We, again, are going to do hypothesis testing and constructing our intervals. How do we do this? Suppose that a simple random sample of size n1 is taken from a population with an unknown mean and an unknown standard deviation. And then we take a second random sample of size n2 with some unknown population mean and standard deviation. As long as the two populations are normally distributed or they have a large sample size, then we could use the t-distribution and, of course, get a t-value and use this lovely formula, which we're not going to use the formula. Again, we'll use StatCrunch to give us the p-values because we like the p-value approach. Biggest thing, though, is that, again, we must know that they're random samples and they're either from normal or they are a large sample size. How do we go about doing this? Well, we can test two means as long as the samples are random. The samples are independent, so there's no relationship between the two here. There's no pairing of data. And the populations are either from normal distributed data or the samples are larger than 30. And again, the samples will be no more than 5% of the entire population. As with all the other examples we've done, the ones I give you will satisfy all of these conditions. So once we've done that, we can move on to our setting up our hypotheses. So when we set up our hypotheses here for independent means, we are going to write them as mu1 and mu2. The null hypothesis is that they're equal, and then the alternate again are not equal to, less than, and greater than. We then have our level of significance, get our p-value. If p is less than alpha, we're going to reject our null hypothesis and state our conclusion. Let's do some examples. In the Space Lab Life Sciences 2 payload, 14 male rats were sent to space. Upon their return, the red blood cell mass in milliliters of the rats was determined. A control group of 14 male rats was held under the same conditions except for space flight. And their red blood cell mass was also determined when the space rats returned. The project resulted in the data listed in Table 3 on the next slide. Does the evidence suggest the flight animals have a different red blood cell mass than the control animals at a 0.05 level of significance? Our sample is 14. That is less than our required 30. So we have to double check that is it normal. So here is our flight rats. Here is our control rats. So in order to be able to run this test, we have to double check if they are normal. So after we enter our data, we would click our normal probability plots and or a box plot. You could then go to the back of the book under the table 6. If you want to use the probability plots, it was table 6. That's for table 6. And see that for 14, you need 0.935. Or you can use this over here. First result is going to be with these guys. We need 0.935. That's So this first one here, the correlation in flight 1 is 0.984. The correlation over here is 0.973, both of which are greater than the 0.935 that was needed to say they were normally distributed. Okay, or you could have just looked at the box plots and said, hey, pretty evenly spaced. They look pretty normal. So I would say, looks pretty normal. I think we can continue on with our discussion. We want to know whether the flight animals have a different red blood cell mass than the control animals. So we want to know, is mu1 no longer equal to mu2? Our null is mu1 equals mu2, and our alternate is mu1 does not equal mu2. So we would go to StatCrunch and we would enter all of our data. And we would get the following printout of a p-value of 0.1627. And if we compare that, our P alpha is 0.05. That is bigger than alpha of 0.05. Are not going to be able to reject the null hypothesis, not reject it. And we do not have enough evidence to show that those flight rats had any different level in their blood cell mass than the control animals. An option like this one, just to show you the difference here, which we've basically done already. This would be one I would enter in both of my columns. So I would have two columns of data. I would go to stat, t-stats, to sample, and I would click with data because I had the data and I would select my two columns. The next example we're going to look at is a summary. So everything we have done so far is with, for the means, when we do the matched pairs, was with data. So we would kind of follow that same setup here. Test whether mu1 is less than mu2 at the 0.02 level of significance for the given sample data. This one doesn't give us data, it gives us a summary. We're going to follow the same process, but instead of clicking with data, we have with summary. So our null is mu1 equals mu2, and our alternate is mu1 is less than mu2. We are no longer doing mean difference. You will actually write mu1 and mu2. We're going to compare p-value to our alpha of 0.02. Summary ones are a whole lot faster to do. Again, we're doing means, so we're going to t-stats. We are now going to sample though. We don't have paired data, so you need to read carefully to know if we are pairing data together or if they are two completely different data sets. So to sample, I've got a summary, and then I'm just going to type what I have. X bar is the mean, so 103.4. Standard deviation is S. Sample size is N. 114.2, 13.2, and 25. Okay, we want to test less than, and we're going to click compute. Not letting me pull it up there. For p-value 0.0013. That is less than alpha, so we are going to reject the null. And we have enough evidence to claim mu1 less than mu2. Walking in the airport. Do business travelers walk at a different pace than leisure travelers? So do they walk at a different? Is mu1 different than mu2? That's what we're testing. Right there, it tells me. Researcher Seth B. Young measured the walking speed of business and leisure travelers in San Francisco International Airport and in Cleveland Hopkins International Airport, and his findings are summarized below. So summary. Is this observational or experimental? And how do you know? It is an observation. He just observed them. He watched them. He timed them. Got their speed. What must be true regarding the populations in order to be able to do this test? Well, we have to know, because if we look at our sample size here, sample size is 20. That's below our cutoff. So we have to know that they are from a normal population. Assuming that the requirements in B are satisfied, do business travelers walk at a different speed than leisure travelers? So I'm going to go back and open up my StatCrunch. I like the summary ones because it's a lot less typing. So T's, sample, summary. 272, 43, and 20. And the second one was 261, 47, and 20. Do know that sometimes when you have independent samples, the sample sizes may be the same, but they may be different. And it doesn't matter because they're totally independent samples. So it doesn't matter if the sample sizes is the same or not. Different. So we want that. There we go. Notice that I never enter anything in these. I am just testing. These all stay 0 because I'm testing for a difference, and no difference is 0. So that's why that stays there. My p-value 0.4448 compared to alpha 0.05. That is clearly bigger. So we are not going to reject the null. If we do not reject the null, we do not have enough evidence to claim business and leisure walk at a different speed. If you want, I can do let me find one of the data so I can show you really quick how we do that. So we're going to look at this example here, which is on an actual data set. And it says researchers wanted to determine whether the reaction time in seconds of males differed from that of females to a go or no-go stimulus. The researchers randomly selected 20 females and 15 males to participate in the study. The go, no-go stimulus required the students to respond to a particular stimulus and not to respond to a different stimuli. The results are as follows. So part A says, is it reasonable to use the t-test and why? Noting that the normal probability plots indicate the data are approximately normal and there are no outliers. So yes, because my sample is 20 and 15. They were random. They said that they came from normal distributions, so we are good to go. B, test whether there is a difference in the reaction times of males and females at the 0.05 level of significance. Let's go back. All right, I'm going to arrow over here. We've got female and male. And anytime you have data, you're going to have to enter it in. we want to do our T to sample, and this time we have data. We are doing females to males, and we want to test, is there a difference? So difference is not equals to here. And we're going to compute. So here's the p-value. P-value is 0.54. That is way too big. We cannot reject. There is no difference here between the two response times. So then it says C. Draw box plots of each data set using the same scales. Does this visual evidence support those results? All right, well, let's see if I can go back here. Let's see if I can. It'll graph both together. If I turn on box plots and I graph them here, well, let's look at that. So it looks like they both reach the same high point here, 0.652, 0.655. So those were pretty close together. The low value here is 0.274, and the low value here is 0.224. So really, if you're looking overall at kind of the spread where the ones hit, the medians hit, I mean, like, even just beginning to end, you can kind of see that both these box plots look to be about the same spread apart. Doesn't look to be different. A difference would clearly show like females on this side, males over here. There would be a distinct difference between the two box plots, and because they're the same here, we really don't have a difference. The last thing we're going to do is our confidence intervals. So remembering that, again, they are random samples. As long as they're random samples, we could use these disgusting formulas, which, again, we're not going to use. We're just going to click in StatCrunch to give us the confidence interval instead of the hypothesis test. Let's take a look at 3 examples here. A Gallup poll of 513 national adults aged 18 or older who considered themselves to be Republicans asked, of every tax dollar that goes to the federal government in Washington, D.C., how many cents of each dollar would you say are wasted? The mean amount wasted was found to be 54 cents with a standard deviation of 2.9 cents. So here's group 1, 513, 54, 2.9. The same question was asked of 513 national adults aged 18 years or older who considered to be Democrats. The mean amount they said to be wasted was 41 cents with a standard deviation of 2.6 cents. Construct a 95% confidence interval for the mean difference. Mean of Republicans minus mean of the Democrats. We have mean, standard deviation, sample size, mean, standard deviation, sample size. Those are just going to go straight into stat, t-stat, to sample, summary. And we will click a 95% confidence interval. We will end up with confidence interval right here. So 12.663 to 13.337 after you enter all of your data in. And then if we were to explain this, we are 95% confident the mean difference in cents wasted per dollar between Republican and Democrat is somewhere between 12.66 and 13.33. We'll see how they say it here. We are 95% confident that Republicans believe the mean amount of each dollar collected by the federal government that is wasted is between 12.7 cents and 13.3 cents higher than the mean amount Democrats believed to be wasted. Okay, so they wrote it a little bit different. They wrote it in a little more common sense terms because both of the values were positive. Showed how much more Republicans felt was being wasted compared to a Democrat. And you can see that here, their average was 54. Their Republican average was 54, Democrat average was 41. So they're estimating based off of some calculations here using a 95% confidence, if we were to access everybody, that Republicans would believe there's a difference of about somewhere between like 12 to 13 cents difference that they believe is wasted more than Democrats. We've got two that we can enter completely into StatCrunch ourselves and interpret. All right, the aluminum bottle, first introduced in 1991 by CCL Container for mainly personal and household items such as lotions, has become popular with beverage manufacturers. Besides being lightweight and requiring less packaging, the aluminum bottle is reported to cool faster and stay cold longer than a glass bottle. A small brewery tests this claim and obtains the following information regarding the time and minutes required to chill a bottle of beer from room temperature, 75 degrees Fahrenheit, to a serving temperature of 45 degrees Fahrenheit. Construct a 90% confidence interval for the mean difference in cooling time for glass and aluminum bottles. All right. This one's a summary, so I'm going to go stats, sample, summary. First one had a mean of 133.8, a standard deviation of 9.9, and a sample size of 42. Right, the second one's mean is the middle one, 92.4. Standard deviation is the bottom one, 7.3, and sample size is 35. We want to run a confidence interval for 90%. And again, we're always looking to see if they're both positive or both negative, or one is more or less than the other one. We look here, the interval 38.13 to 44.67. 38.13 to 44.67. Okay, they're both positive, and the way we entered them is we did glass first and aluminum second, and the result was positive. So positive means the first one is larger than the other by this much. We are 90% confident that a glass bottle takes on average 38.13 to 44.67 minutes. Yep. Longer to cool than an aluminum can. Okay, so that's written more real world. You could follow our basic setup of we are 90% confident the average difference in cooling time between glass and aluminum is between 38.13 and 44.67 minutes. Remember, you can write it more classical, kind of following the basic setup of we are blah, blah, blah percent confident that the average difference of whatever it is we're looking at is between the two values, or you can make it make a little more logical real world sense of, hey, these are both positive. So we found with 90% confidence that glass takes this much longer. If these were smaller, if they were negative, then they would be faster than aluminum. And you can see here, look at the difference. On the mean, 133.92. That's almost a 40-minute difference, as you could see just from the means here, which is around what we found in our interval. Stocks may be categorized by sectors. We're going to open a data file 11.319. So let's see. The data represents the 1-year rate of return for a sample of consumer cyclical stocks and industrial stocks for December of 2013 to November of 2014. So an entire year of return of stocks. So consumer cyclical stocks are things like Starbucks, Home Depot. Industrial are places like 3M and FedEx. So can we construct a 95% confidence interval for the mean difference in rate of return between these two stocks? If I want to find one of these, I need to go to Pearson. I'm going to log back in here. I'm going to go to StatCrunch. Data sets from textbook. I want 11.319. So chapter 11, 319. Here's all my consumer cyclicals, and here's my industrials. We have a bunch of them. We have 96 here and 98 here. Totally different data sets. The sample's large enough. Going to have a normal distribution, so we will use our T to sample, and this time we have data. So consumer cyclicals, industrials, and confidence interval 95%. So this one is negative 13.94 to negative 1.72. All right, so you've got negative 13.94 to negative 1.72. The last one, we had positives. Positives meant first was bigger. So if they're both positives, first is bigger than second. When they're both negatives, first is smaller than second. We are 95% confident. I'll do the basic one first. The mean difference in stocks is between negative 13.94 and negative 1.72. Okay, to have this make more sense, this is consumer cyclical, this is industrial. We are 95% confident the mean rate of return of consumer cyclical stocks is, I'm going to do it the other way, smaller to bigger, 1.72 to 13.94% less than the industrial. 95% confident the mean rate of return of the consumer stocks is that percent less than industrial stocks. Yeah. If you got one that was one negative and one positive, then that means in the end, there is no difference overall, but we would then go to something like this. Pretend our result was negative 10 to 5. Let's just say that's what it was. We would have to go to this first one. We are 95% confident the mean difference in stocks is between negative 10 and 5%. Okay, so what that means is we can be anywhere between the one is percent less to over 5% more. It's on both sides, meaning that overall there's no difference between the two. Review slide here. If we are working with a proportion, the only one we are doing here is independent. We're going to do proportion stats. We are not doing standard deviations with the samples. Means we did both independent and dependent. Dependent uses t-stat paired. Remember, this is matched pairs. Independent is t-stat to sample. You have to make sure when you're doing a t-stat with two samples, you double check, are they independent, totally different random samples, or is one based off of the other dependent? All right, so this is the end. This is the end of statistics. You are not going to learn anything more after this. If you have any questions about any of this, please reach out, send me an email, and I will get back to you. All right, I hope you had a good semester, and if you need anything in the future, don't hesitate to ask.